Now, moving on to the next example. So first of all, please change this to example number 7. This is not supposed to be 14, so change this to 7. And once again, in this example, we are supposed to use the substitution technique to solve a double integral. So let's take a look at the double integral we have in this problem. So here we have a square root of x plus y times y minus 2x squared. And that is the multi-variable function that we are supposed to work with. So let's write that down right here. Function of x, y equal to square root of x plus y times y minus 2x squared. Alright, now let's take a look at this dy dx. Of course, this is the differential area, dA, expressed in terms of x and y. Now, let's take a look at this function that we have right here. By the look of this, with all these terms, I think this is a little bit too complicated for my taste. You can choose to solve this double integral as it is, working with x and y directly, just like what we did before. But it's going to be tough, right, with all the square root and the square. So, if possible, I would like to simplify this function to be something that is simpler. And it's a good chance for us to use the sub technique that we just learned. So, once again, we are going to simplify this function f of xy into a new one, a newer, easier version of this. So, we are going to change this to a new function g that is supposed to be less complicated. And once again, this g is going to have new variables. So, we start with two variables, x and y. In the end, we are going to end up with two new variables. Just like in example number 6, here we are going to have u and v as the new variables. And now we are going to perform the sub in order to simplify f of xy. So let's take a look at the f of xy that we have right here, the square root and the square. Looking at all these terms, I would like to put u right here. To simplify the inside of this square root, I'm going to put u to replace x plus y. So that is the first sub. So u equal to x plus y as our first sub. And then I still have v to play with, right? So I choose to put v inside this parenthesis to simplify the inside of this square. So here I assign v to be equal to y minus 2x. So v equal to y minus 2x. So there you go, the second sub. And now we have got the simpler function to work with. So let's put everything in. Function of g with uv as variables is going to be equal to the square root of u. So I'm going to put u right here. Square root is 1 over 2. Alright, times v squared. Times v squared. And that is our new function. Okay, so let's put a box around that because we are going to use that for sure. So what we did right here is the first step, which is to simplify. Okay, and we are done with that. Now let's move to the second step in the guideline, which is to transform the differentials. We start with dy dx. We need to change it to the differentials in terms of u and v, right? So we need du dv, and once again we only need one formula to do that. So it's going to be this formula again, dx dy or dy dx, doesn't matter, dx dy equal to the Jacobian determinant. So we are supposed to find the Jacobian matrix and find the determinant of that, and times with du dv, and there you go, we can have this transformation from xy to uv. Okay, so we need this Jacobian matrix, and the first step to find this Jacobian matrix is to construct a vector function. Without a vector function, you cannot find the Jacobian matrix. So let's start with that. The vector function that we need is going to be based on the relation between the original variables x and y and the new variables u and v. So it's going to be based on this u and v right here, two subs. And we are going to put everything in this form that we had before in the guideline and in example number 6. So we are going to express the original variables x and y as a vector. And then we are going to balance this equation as the function of the new variables. So it's going to be a vector again, and we are going to express x in terms of the new variables. Function f1 of uv, new variables. Same with y. f2, a different one. u and v again. So we are supposed to find these f1 and f2. Okay, so we are going to work on this one first. X in terms of u and v. So I'm going to make use of this sub that we have right here. U equal to x plus y, right? So I'm going to try to put x alone on the left-hand side of the equation. So let me work on that further right here. Sorry for the space. So looking at this one, first one is u equal to x plus y. So moving, what about I put this again right here, u equal to x plus y. And now I want x to be alone on one side. It's going to be equal to u minus y, right? And I cannot use this right away because I still have y inside this equation. What I need right here is in terms of u and v only. So I need to get rid of this y. To get rid of this y, I'm going to use this sub right here. V equal to y minus 2x, which means that y is going to be equal to v plus 2x. And I'm going to put that right here. Y equal to v plus 2x. So in the end, I have this u minus v plus 2x. And I need to move things around, and in the end, I can separate x to be alone on the left-hand side, and that is equal to u minus v over 3. U minus v over 3. And there you go. We have this first relation between the original variable x and the new ones, u and v. And this one is f1. So this equal to, first one, we have got that x equal to u minus v over 3. Now, we have to do the same for y. We need to find this y in terms of u and v. I'm going to start with this one again. U equal to x plus y, right? So I'm going to put y on one alone on one side. It's going to be y equal to u minus x. And I don't want x right here. I want it to be in terms of new ones. So I know that x equal to u minus v over 3. So let's use that. So here, y is going to be equal to u minus v over 3, coming from this equation above. So in the end, this y is going to be equal to 2u plus v over 3. So there you go, y in terms of the new variables. Okay, so y is equal to 2u plus v over 3. And there you go, that we have the complete vector of the two functions. So you can say that this is the vector function that we need in order to find the Jacobian. Vector function, and we got it from the two subs that we assigned earlier. So now that we got the vector function, let's proceed to find the Jacobian. And once again, Jacobian is the first derivative of the vector function with respect to all the variables that we have. So it's going to have this form. 2 by 2 matrix for this problem because we have two variables. First function with respect to first variable. First function with respect to the second variable, v. Second function, f2 with respect to the first variable, u. And same for the this one, f2 with respect to last variable, v. Okay, we need to find this. Alright, so let's work on this one by one. Let's start with this, Let's start with this first one. Diff F1, okay, Diff F1 with respect to u. So I'm going to work on this one. F1 is right here, and we need to diff this with respect to u. Diff this term with respect to u, we are going to get the coefficient in front of u, right? And that is 1 over 3. Okay, 1 over 3 right here. And now we move to this diff f1 with respect to v. and we diff the same term right here, same function right here with respect to v, and the coefficient in front of v here is minus 1 over 3. So there you go, we got the second element for this matrix, minus 1 over 3. Now let's move to next one, diff F2 with respect to u. So we need to diff this with respect to u, and the coefficient is 2 over 3. Okay, 2 over 3 right here. Now let's diff this. Find this F2 with respect to v. Let's diff this with respect to v. We get 1 over 3. Alright, so that is the complete Jacobian matrix. And now what we need to do is to find the determinant of this so that we can put it in the formula. So next step, we find the the determinant of this Jacobian. Alright, equal to, cross down, that is 1 over 9. Okay, so we have 1 over 9 for the first term, and then cross up. Okay, minus 2 over 9. So it's going to be minus the cross up, which is the minus 2 over 9. So here we have this 3 over 9, or you can say it's 1 over 3. Okay, and that is the Jacobian determinant. So let's put this into the formula, and now we have this relation between the original differentials and the new differentials, dx dy equal to the Jacobian determinant. We just got it right here. So 1 over 3 times the new differentials. So 1 over 3 right here, and the new differentials are du and dv. Okay, now we are done with the second step, the transformation of the differentials. So let's put number 2 right here. We just got that done. Now let's move to the last step, which is to translate the boundaries. So we are going to take a look at the boundaries that we have, 4 of them. Lower bound for y, upper bound for y, lower bound for x, and upper bound for x. So let's bring everything down here. So I'm going to start with the one inside, which is the y variable. Lower bound for y is going to be equal to 0. First one, y equal to 0. Upper bound for y, that is y equal to 1 minus x. Okay, and we have to work on the x variable too. Lower bound for x, x equal to 0. Upper bound for x, x equal to 1. And we cannot use them because right now we are working with u and v. So our job is to translate all of these into u and v variable. Okay. So let's take a look at the first one right here. Y equal to 0. So we need to change this into u and v, right? So I'm going to make use of this. Y equal to 2u plus v over 3. Let's use that. So y is equal to 2u plus v over 3. And from this equation, this is supposed to be equal to 0. So we can cancel this 3 away, and in the end we have this relation. V equal to minus 2u as the first boundary in terms of v and u. Okay? Okay, at this point I want you to compare the result that we got for this translation to the ones that we have for the example number 6. In example number 6, all the boundaries are just constant values, right? U equal to 0, u equal to 1, v equal to something. But here we got something different. We got an equation with both v and u in there. We don't have a constant in this, which means that this is going to be a little bit different from example number 6. What you see right here is a straight line in the space of u and v. Okay, so let's make a note right here that the boundary that we got right here is a line, straight line. Okay, this is a straight line in two-dimensional UV space. Once again, we are no longer in x and y, so this is going to be a line in UV space. And as you can see, this is going to be a straight line with a slope of minus 2, with u as a horizontal axis and v as vertical axis. Okay, and we are going to see the shape of that later. So let's keep that in mind, that this is no longer a constant. This is a line instead. All right, let's work on this second one. y equal to 1 minus x. So once again, y equal to 2u plus v over 3. And equal to, oh, what about I do this instead? What about I move x to the other side? So this way should be easier. So moving x to the other side, I have this x plus y equal to 1. And from above, right here, x plus y equal to u. So I can just use this right away. So this, in the end, is just u equal to 1. Alright, so u equal to 1, and let's put a box around this. That is the second boundary. This boundary is more simple because this u is equal to 1, just one constant. So make a note, this is a simpler boundary, simpler version, which is a constant. Okay, now let's move to x equal to 0 right here. X equal to 0, and I know that x equal to u minus v over 3, so let's use that. So x equal to u minus v over 3, and it's supposed to be equal to 0. So in the end, I have this equation v equal to u as the third boundary. Once again, we have an equation again. It's not a constant like this, u equal to 1. So make a note, once again, this is line in UV space. Okay, and we are supposed to draw them later. Now, last one, x equal to 1. We have this x equal to u minus v over 3 again. So u minus v over 3 equal to 1. Alright, so moving things around, we have this v equal to, okay, u minus 3. Okay, so let's put that right here. V equal to u minus 3. And once again, we have an equation of between v and u. Once again, this is lined in UV space. Okay, now we got everything. We simplify the function, we transform the differentials, and we translate the boundaries. Now all the boundaries are in terms of u and v, but at this point we don't know which one are the upper bound or the lower bound, because it's not just a simple constant that we had in example number 6. In order to determine the lower bounds and the upper bounds, we are supposed to draw them in the space and determine the integration domain, and we are going to do that in the next slide. Okay, so we are going to work on these four, draw them and determine lower bounds and upper bounds. So let's move to this. It's already drawn for you, but I'm going to repeat that. But anyway, let's put all the information in this slide again. So I don't want to move between two slides constantly. So let's work on the information that we have from the previous slide. Number 1, the simplification of the function. Now we have got the new function in terms of u and v, and that's going to be g of u and v equal to the square root of u to the power of 1 over 2 times v squared. Right? Second one, the transformation of the differentials. We found dx dy to be equal to 1 over 3 du dv. No problem with that. Now the translations of the boundaries, number 3. Okay, so the first boundaries that we got from the previous slide is going to be this v equal to minus 2u, first one. Second one is a simple one, u equal to 1. Alright, this one should be easy. Now next one, back to an equation of line u, well, I can put v equal to u. Same thing, v equal to u. And the last one, also aligned, v equal to u minus 3. V equal to u minus 3. Okay, now we have all of them here. We are going to draw them on a graph. So let's start with this one, v equal to minus 2u. Now we are going to work on the space of u and v. As you can see here, there is no x and y anymore, so we are going to put u and v on axis. As you can see here, u is going to be on horizontal axis and v vertical axis. And now we are going to plot this. V equal to minus 2u. And as you can see here, this is equivalent to y equal to minus 2x. So it's going to be a straight line with a slope of minus 2. And it's going to correspond to this line right here. A straight line with a slope of minus 2. Okay, I didn't do a good job, so let me fix that. So this straight line, okay, a little bit better. Let me highlight that. That is the first boundary that we have. It's a straight line with a slope of minus 2. And that is the equation that we have for that line. Okay, v equal to minus 2u, and that is the first one. So let's move on to the next one. This one is simple. U equal to a constant value of 1. So it's going to be this. U right here equal to 1 right here. So it's going to be this line. Straight, constant, u equal to 1. Second boundary. Alright, now let's move to the next one. V equal to u. And this is just simple, y equal to x. So we get this line right here, y equal to x, v equal to u. Okay, straight line, slope of 1. And the last one, right here, v equal to u minus 3. This is a straight line with a slope of 1 crosses v axis at minus 3. So let's find minus 3 first. Should be around here. I'm going to say around here. Again, minus 3. I'm going to extend the v-axis down here. So it's going to be a line with a slope of 1 crosses this v-axis at this point, and it's going to be this line. Okay, something like that. Parallel to the v equal to u. And now we are supposed to find the integration domain trapped between these four lines. And as you can see, I think you can tell that it's the region D right here. It's going to be this integration domain that we are supposed to perform the integration on with the sub technique. Alright, so now that we have the region, the next thing we are supposed to do is to determine the order of the integration. So let's construct the double integration that we have for this problem. First of all, we have this. Okay, let's put this double integral. And we change the function to be this newer one. It's going to be u to the power of 1 over 2 and v squared. And we have this 1 over 3 du and dv. du, dv. But it turns out that the order of this du dv, the order of this integration can be swapped. So we need to determine whether we want to use dv du or du dv. So that is the question that we need to answer. You can pick one right away, but maybe one of them is easier to work with. So, or dv du. Now you have to ask yourself, how do you want to sweep this integration domain right here? You want to sweep it du first. If you sweep du first, you are going to have this sweeping pattern horizontally, right? Or you want to sweep v first, which means that you are going to sweep the region vertically first. Alright, so let's take a look here. If you decide to, what about I change the color over here now that you know that this is the region that we are supposed to work on. If you decide to sweep u first, like what we have right here, we are going to sweep horizontally first. So you are going to do this, sweeping from the left boundary to the right boundary. So it's going to be like this all across the region. But there is a problem with that, because as you can see here, the lower part right here starts from the red line. As you can see, this one starts from the red line. But when you move to the upper part of this region, you are going to start with the black line, and it's going to be a different function to work with. So this might not be a good idea, so why don't we try something else? The other way. We are going to try to sweep this vertically first. What's going to happen? So if we decide to sweep this vertically first, we are going to start from the red line and ends at the black line. And it's going to be the same all across the region. And that is good, right? So we don't need to switch the equations. Which means that we are going to assign the red line as the lower boundary for the sweeping for v variable. Oh, by the way, from the sweeping pattern that we have right here, we decide that dv du is going to be the choice that we picked, right? Because v right here is the vertical sweeping. Vertical sweep. So I'm going to change this to dv du instead. So this one, I don't like it, so change it to a new one. U to the power of 1 over 2 v squared 1 over 3. And we have picked the order of the integration. Start with dv to sweep the v direction first, and then du. Now we are supposed to find the boundaries for the integration sign. So let's take a look here. I'm going to change this a little bit. So we are supposed to find the lower bound for the y variable right here. Y equal to what? Okay. Oh, I'm sorry, not y, v. V equal to what? And ends at v equal to what? And for u, start at what value and ends at what value? So now we are supposed to find the lower bound for v value. And it's going to be this line right here. Lower bound for v value. This line. Straight line. Okay? You see that, right? And it's going to be this equation, and it says that v equal to minus 2u. So this line is the lower bound for v variable, and it's going to come into play right here. V equal to minus 2u, the straight line of the lower boundary of this region. And what about the upper bound of the v variable? It's going to be this black line, right? This is the upper part of this region. And this line is v equal to u, so we are going to use this equation as the upper bound for v variable. V equal to u. Okay, now that we are done with the sweeping vertically, we are going to look at the u variable. And we can see that u starts from 0. Oh, I'm sorry. That u starts from 0 and ends at 1. So the range of u from 0 to 1. So let's put that into the integration sign. U start from 0 and ends at 1. Now we got everything. Functions in terms of u and v, differentials in terms of u and v, the order that makes integration easier to work with, and all the boundaries in place. From now on, we just proceed with the integration normally. So we are going to integrate this with respect to v first. So first of all, I'm going to take 1 over 3 outside. Alright, so we have 1 over 3 right here. And integration of u squared, square root, and v squared. And we have dv first, and then du. Start at v equal to minus 2u. This line, the red line, ends at the black line. V equal to u. U, the range of u starts from 0 and ends at 1. Okay, so this is going to be equal to, let's integrate this with respect to v. So this, with respect to v, we get v cubed over 3. So 1 over 3, everything is still the same. Okay, what about I put this right here? So u right here, the same u with the power of 1 over 2, and v here becomes v cubed over 3. And I need to evaluate this at two values of v, and that is v equal to minus 2u and v equal to u. And I still need to integrate this one more time with respect to u. Okay, u starts from 0 and ends at 1. Okay, at this point I want to move this 3 outside. Alright, I like to combine all the constant and move it outside of the integral to keep things simple. Alright, so this is going to become 1 over 9. Okay, now I need to evaluate this v at equal to u, right? So u is going to go into right here. So 1 over 9, integration from 0 to 1, so u 1 over 2, alright, u goes in, it becomes u cubed minus, alright, and then this minus 2u equal to v goes in as v. So it's going to be, this one is going to be minus 8u cubed, alright, and integrate this with respect to u. So in the end we have this 1 over 9, integration from 0 to 1, u to the power of 1 over 2, nothing changes here, and from the inside we have this 9 u cubed, alright, and this 9 right here cancel with the 1 outside, so we are supposed to integrate this u to the power of 1 over 2 times 3. Let's continue over here. It's going to be equal to integration from 0 to 1 of u to the power of 7 over 2. Combining all these power becomes 7 over 2. Integrate this with respect to u. So here equal to u to the power of plus 1 to that, it becomes 9 over 2, right? Divided by this term, it's going to be 2 over 9. And evaluate this at 0 and 1. Okay, so 1 goes in, this becomes 2 over 9, and 0 goes in, equal to 0. So in the end, we have this 2 over 9 as the answer for this example. Okay, so that is it. This one is a little bit different from example number 6 in the way that the boundaries are lines, not constant. Okay, but in the end, it's the same guideline, same process. Now let's move to the last example of this lecture. Alright, first of all, please change this to example number 8. Okay, this one to 8, and in this example, once again, we are going to use the sub technique to evaluate an integral, but instead of a double integral, we have a triple integral in this problem. Alright, so this is going to be a little bit different. So let's take a look at the triple integral that we have right here. This is the multi-variable function in terms of x, y, and z right here. Okay, let's write down that function right here. F of x, y, z equal to 2x minus y over 2 plus z over 3. Alright, and dx, dy, dz, of course, this is the differential area in terms of x, y, and z. Looking at this function is not that complicated. We can work on this directly without having to use sub technique. But let's assume that I am not happy with this. I want to make this simpler. Okay, so we are going to try to make this f right here simpler than it is. And I'm going to change this to g again. And this g is going to have 3 variables, u, v, and w. And now that I have 3 new variables, u, v, w, I have to find a place to replace them in the original function to make things more simple. So I can pick any places I want, but what about I try to put u right here? This whole term, I want to simplify it to be u. And I can choose z over 3 to be v, but what about I try w? That can be done. And I still have v left. What about simplifying this y over 2 to be just v? Alright, so now we have 3 subs. First one, u equal to 2x minus y over 2. Second sub is v equal to y over 2. And last one, w equal to z over 3. Okay, now that I got all of them, what about I complete this function right here, function g. Function g is going to be just u plus w. You can pick different places for the u, v, w, that's up to you. There is no right or wrong. Okay, so now that we got the new function, let's proceed to the transformation of the differentials. Okay, that is the first step that we need. Simplify the function. Okay, so we have just u plus w now. Okay, let's move to the transformation of the differentials. Once again, we have this dx, dy, dz, the original differentials, and it's connected to the new differentials with the Jacobian determinant. Same formula. Jacobian determinant of du, dv, and dw. Okay, a little bit different from example 6 and 7 in the way that we have one more variables for both the original and the new ones. Okay, so once again we need to find this Jacobian, and we are going to start by constructing the vector function that connects the original variables xyz to the new variables uvw, and it's going to be the same form. With this vector, instead of x and y alone, we have z as well here, and it's going to be equal to, alright, f1 of 3 new variables u, v, w, f2 for y, 3 new variables, and same for z, and we have f3 for that, u, v, and w. Okay, let's start with this. We are supposed to find f1, f2, and f3. So f1, I'm going to start with this relation right here. I'm going to try to put x alone on one side. So from that, let me continue over here. So I have this u equal to 2x minus y over 2. Moving things around, I have this x equal to u plus y over 2. And I cannot use this because I still have y in there. And I notice that y over 2 equal to v. So this is equal to v. That's good. So I have this x equal to u plus v. X expressed in terms of new variables u and v. So that is f1. Okay, f1 is u plus v. What about f2? Y in terms of the new variable. Looking at this, I can just move 2 to the other side. I have y equal to 2v. That's it. That is f2. Y equal to 2v right here. This one is easy. So f3, z in terms of the new variables. Looking at this, and I can see that z is equal to 3w. Z in terms of the new variable. Z equal to 3w. So there you go, we have the vector function connecting original variables and the new ones. Right, vector function that we need for the Jacobian. Alright, and let's work on the Jacobian right here. So Jacobian is going to be equal to, once again, the partial diff of the vector function with respect to all the variable. So I'm going to, repeat the formula again. Diff F1 with respect to the first variable. Diff F1 with respect to the second variable. And to the last variable. And repeat that for F2 and F3. Partial diff of F2 with respect to first variable. F2 with respect to V. F2 with respect to W. And the last row, F3 with respect to U, and F3 with respect to V, and F3 with respect to W. Okay, this is long. Okay, let me fix this one. Make it a little bit nicer to look at. So, alright, now we are supposed to find all of these 9 terms. So let's take a look at what we are going to get for each one of them. We are supposed to, let's start with this one. Diff F1 with respect to u. Okay, so we are going to diff this with respect to u. What do we have there? Coefficient in front of u, that's going to be just 1. Easy. So let's move to the next one. Diff F1 with respect to v. Diff the same function again with respect to v. We got the coefficient in front of v, that is 1. Now, do the same for w. Diff this same function with respect to w. We don't have w here, so we are going to get 0 out of them. Okay, not too bad, right? So let's move to F2. F2 with respect to u. This one with respect to u, there is no u here, so I get 0. F2 with respect to v. Okay, F2 with respect to v. Diff this with respect to v, we get 2. Okay, and last one, diff F2 with respect to w. F2 right here, same one, with respect to w. No w here, of course, that is going to be 0. Now, last one, F3. Diff F3 with respect to u. Diff this one with respect to u, of course, I get 0. Diff this one, F3 with respect to v. No v there, also 0. Now, diff this same function with respect to w. Last one. This with respect to w, we got the coefficient 3 out of that. So there you go. We have this Jacobian matrix, complete one. Now, our job is to find the determinant of this. So, determinant of this Jacobian matrix. We are going to cross down this. Okay, let's use green. Crossing down, we have 6. Okay, so the first term is 6. And cross down, 1 to 0. So everything goes away. 1 to 0, and right here, nothing. 0, cross down right here, also 0. So we only have 6 right here. Minus, crossing up, cross up. This is going to be 0. This also 0. And last one also 0. That is easy. So let's put 0 there. So in the end, we have this Jacobian determinant equal to just 6. And now we have the relation between the original differentials in terms of the new ones. Okay, we have this dx, dy, dz equal to the Jacobian determinant. We just found it to be 6 times du, dv, dw. Okay, so we need this. So let's put a box around this one. Okay. All right. Now we are going to. By the way, we are done with the transformation of the differentials, number 2. Now we move to the translation of the boundaries. It's going to be long because we have 6 of them. So I'm not sure if we have enough space. So let me squeeze things in. So 6 of them. Let's start with the one for the x variable. So, as you can see here, lower bounds for x, y, z, and the upper bound for x, y, z. Let's start with the one inside. Lower bound for x, that is x equal to y over 2. That's the first one. Lower bound for x, and upper bound for x is going to be x equal to y over 2 plus 1. And let me continue over here. All right. So we have the lower bound for y, that's y equal to 0. Upper bound for y equal to 4. Lower bound for z equal to 0. And upper bound for z is equal to 3. We are supposed to translate all of them in terms of u and v. Okay? Alright, let's do that. X equal to y over 2. So, by the way, let's take a look at this right here. X equal to u plus v. Let's use this up here. X equal to u plus v. So this is going to be u plus v equal to y over 2. And y over 2 equal to v. So there you go. This is going to cancel, and we get this nice boundary with constant value. U equal to 0. I like it because this is easy to work with, right? Instead of a line in UV space. Oh, in this case, it's going to be UVW space. So this is a constant boundary, easy to work with. Constant. All right. Now let's take a look at the next one. This one, x is equal to u plus v again. And we have y over 2 equal to v, and we have plus 1. So this cancels with that. Once again, we have a constant value of u equal to 1. All right. So from this, definitely, u equal to 0 is going to be the lower bound for u variable. Low for u. Okay. sorry for the space, and this one is high bound, high for u. Okay, for u. Now let's move to y equal to 0. Y equal to 0, and change this into in terms of UVW. So this one, alright, y is equal to, let's take a look here, y is equal to 2v. So this one is 2v equal to 0, which means that we have this v equal to 0 as the next boundary. Okay, now next one, y equal to 4, and y is equal to 2v equal to 4, which means that v is equal to 2 right here. And from this, both of them are constant, and one of them is lower than the is less than the other one. So this is clear that this is low bound for v, and this one is high for v. Okay, let's move to the last two. So here we have z equal to 0. So z equal to 3w. Let's take a look here. Z equal to 3w. So let's put that into this equation. Z equal to 3w, and it's supposed to be equal to 0. So in the end, we have this w equal to 0 for the next boundary. Okay, and last one, z equal to 3. And once again, z is equal to 3w. And 3w equal to 3, which means that w is going to be equal to 1. And once again, we have constants for the boundaries for w. This one is low for w, and this one is high for w. Okay, I don't like that. Let me fix this. This one is high for w. Now I want to conclude all of these boundaries that we found. We found that u has to be over this range from 0 to 1, coming from these two boundaries. Right? When you have a constant or a boundary, it's kind of easy to work with. Now for v, supposed to be in between 0 and 2 from here. Okay, and last one, w, to be in between 0 and 1. Okay, now we have got everything. Simpler function, new differentials, and the new boundaries. And let's just solve the triple integral in terms of the new variables in the next slide. Okay, we don't need all this space. So let me put all the information right here again. Number 1 is the new function. Okay, so we have this new function g of u v w equal to just u plus w. And we have this differentials between the old ones, the original ones, and the new ones. dx, dy, dz equal to the Jacobian determinant. We found it to be 6. And new differentials, du, dv, dw. And the boundaries, okay, all of them. U in between 0 and 1. Okay, U between 0 and 1, and V between 0 and 2. Okay, 0 and 2. And last one, W between 0 and 1. Okay, as you can see here, we have the constraints, the boundaries that are constant. So you can pick any integration order that you want. So I'm going to construct the triple integrals down here. So we are going to have this triple integral. On the new function that we have, it's going to be u plus w. Okay, this is the new function. And with respect to the new differentials, and we have the 6 right here from the Jacobian determinant, and we have du, dv, and dw. We pick this order in random. You can choose different order, that doesn't matter. What matters is the boundaries that you put into the integration sign that correspond to the right differential. So the first one is going to be for u. Alright, And we know that u is supposed to be in between 0 and 1. So u starts at 0 and ends at 1. Alright, and now for v, starts at 0 and ends at 2. And last one, w, start at 0 and end at 1. Okay, w starts at 0 and ends at 1. You can pick different orders if you want to. Alright, let's proceed with this triple integral. Okay, first of all, I'm going to take 6 outside. Right, I'm going to take the 6 right here to the outside of the integral. And let's work on this. I am going to integrate this with respect to u. Alright, so I'm going to get u squared over 2. From that, I get u squared over 2 plus wu. And I'm supposed to evaluate this at two values of u, 0 and 1. And I still have two integrals to work with respect to dv and dw. v from 0 to 2 and w from 0 to 1. I still have 6 right here. Okay, 1 right here goes in, here and here for u. Okay, what do I get here? 1 goes in, I have this 1 over 2 plus w. Alright, and 0 goes in, gone. Same thing here, so I don't need to worry about that 0 terms. So here, we are supposed to perform double integral on this one. Okay, with respect to v first, and then to w. And from 0 to 2 for v, and 0 to 1 for w, and we still have 6 outside. So let's continue that over here. We are going to integrate this with respect to v. So here we are going to get this v over 2 plus wv. And we are supposed to evaluate this at two values of v, from 0 and at 0 and at 2. Still need to integrate this one more time with respect to w. And from 0 to 1. And we still have 6 right here. So 2 goes in as v right here and v right here. So let's take a look at what we have. So here we have this 2 over 2, that's going to be 1. And we have this 2w. And when 0 goes in, everything goes to 0. So no problem with that. Okay, so in the end, we only have this 1 plus 2w. And we are supposed to integrate this with respect to w. Okay, so 0 to 1 with respect to w. So what do we have here? 6 still outside. Integrate this with respect to w. We have this w plus w squared, right, to cancel with each other. So this from 0 to 1. Okay, so here 1 goes in, we have this equal to 6. 1 goes in, we have this as 1 and 1, so this is equal to 2. And now 0 goes in. Everything goes to 0, so I don't need to worry about that. So in the end, I only have this 6 times 2, and it's equal to 12, and that is the answer for this example number 8.